Welcome back. In the previous lecture, we had shown how any kth order ordinary differential equation, the solution to a kth order ordinary differential equation can be seen as a fixed point of some operator. Basically, you can reduce any kth order ordinary differential equation to a system of first order ordinary differential equations, and then the solution of a first order ordinary differential equation can be seen as a fixed point of some operator. In this lecture, we are going to prove the existence of these solutions using the fixed point results. So firstly, this is something which we had finished with the previous lecture. We had seen that as a consequence of the contraction mapping theorem, we have the Banach fixed point theorem, which tells us that if you have an operator from a board of radius r, which is contraction, then you have a unique fixed point. Consequent to this, we are going to prove this result, which shows the existence of a unique solution to an first order system of ODE. So you see, this is called an initial value problem because you have first order ODE. So usually, if you have a kth order ODE, to get a solution, you need k conditions for well-postness. So for a first order ODE, you have one condition, but here the one condition, the value of u is given at some point. So this is called the initial value problem. If you have a second order ODE here, you will have you need two more. You need two conditions. So you can impose. So you fix a point. In this case, it's 0. The value of u at that point, and the value of the derivative of u at that point for a second order, and so on. So for a kth order, you need to give the value of u up to k minus 1 derivative. These are called initial value problems. Later we will see, probably in the next lecture, we will see in the second order case, there is a different kind of, which is called boundary value problem or 2-point boundary value problem, where you give the value of u at two different points for second order instead of giving the value of the derivative of the function. Okay, so this is an initial value problem. So this existent result is for initial value problem of a first order system of ODE. So what is this theorem saying? That if there is a capital T and f, which is the data here for the ODE, if the f is a continuous function in both the variables, right? F is a continuous function in both the variables, that is in the t variable and the second variable here. Now it's because it's a system of n equations, you have power n here. Okay. Okay, and the u is also is n vector, so the value of ut will be in Rn, and this f satisfies the Lipschitz condition in the second variable. Okay, so this f has this Lipschitz condition. So for all t and all xi1, xi2, you have this result. Then for any given vector u0, which is some fixed vector in Rn, which is the initial condition. So given f, which is Lipschitz, and given any vector u0, and this problem, which is 10.1, the system of first order ODE has a unique solution, which is in C1 of 0t, which is continuously differentiable function extended up to the boundary. The derivative can be extended up to the boundary. That's what this says. So C1 0 cos t. So we need to prove this result. This, in the modern version, the Cauchy-Lipschitz or Picard-Lindelof theorem, Picard's theorem, and all these are same theorem, same results, which basically shows the global existence. So here you see you have a solution u in the entire region. So the f is given in the entire region, and that is 0t for all time t, right? For all t. So the time usually can, the t can usually denote time. Okay, so what this result is saying is showing the existence of a unique global solution for this problem under the Lipschitz assumption of the f, which is the data. So to prove this, we define this operator t from the space of continuous functions to the space of continuous function. Now, because we are in a system of equation, we have the power n here, right? The Cartesian products of, the n copies of the space of continuous functions, because these are all now n tuple vectors, right? U, this bold U. So this is a map that we define, which takes any element U from here and gives this function U, right? This is what we have seen in the previous lecture, how this problem, solving this problem is equivalent to finding the fixed point of this problem, right? Because if you have a fixed point for this problem, then you have U, which is Tu equal to U, which is precisely what solves this. So you define a T like this. We need to show this T has a fixed point. Our aim is to use the contraction mapping theorem or the Banach fixed point theorem. So if T has a fixed point U, then we have already argued that the U solves 10.1, right? We have already seen in the previous lecture. So we first show that T is a contraction map. So to show that T is a contraction map, we are going to tweak the subnorm here a bit, okay? So we are going to consider an equivalent norm, and we are going to show the contraction in that norm, okay? We can also do it in the usual subnorm, but then you have to keep track of things. I will mention about that later. So we give this space of continuous function a tweak in the subnorm. That is usually we take the case when alpha is 0, that is a subnorm. In this case, we are going to add a weight. So this is like kind of weighted norm, okay? We are going to take some fixed n alpha, and we are going to look at e power minus alpha t mod of vt. This is the norm that we are going to. So for any element here, v here, we are going to define norm alpha as supremum over this product. Okay, this is a norm that we can give. Now this norm is equivalent to the subnorm. Okay, that is because we can see that this norm has this relation e power alpha t of subnorm is less than this alpha norm, then this alpha norm is less than subnorm because this is less than 1. Okay, so with this inequalities, we actually have this norm alpha is equivalent to the subnorm. So basically the topology is same. Though we have a different norm here, the topology is same. We are not changing that. So it's a complete Banach space. Everything will work. Okay, everything remains true. So C0T is a Banach space, right? Because they are equivalent norms. So we are going to work with this norm. Now the reason why we are looking at this norm, not the usual norm. Usual norm also we can take. That's what I'm saying here. That one can consider the usual norm, usual subnorm, right? But in that case, proving T is contraction is not going to help you much. We need to show that T power K is a contraction for some very large K, and then whatever we are doing in this proof, we just proceed in that way. It's just that we have to find it may fail to be contraction for T, but you can find some large K for which T power K will be a contraction, and then we can use the fixed point results. So just to avoid that kind of a complication, we have just considered an equivalent norm on the space of continuous functions. So to show contraction, we look at TV minus TW for two different V and W, right? So we look at this now. So by definition, this is this, right? And then now this is in the right, TV is here. So TV minus TW, T is defined like this. TV minus TW, this U naught will be cancelled. So you will have your interval from 0 to T, f of V and F. So you will have Fu minus Fv, right? That's what we have here, Fsv minus Fsw, sorry, Tv minus Tw. We have just multiplied and divided by e power alpha s here, okay? This is just, right? So we just added, we have just multiplied and divided this. Now this, in this, now we take this quantity and take supremum of that, which is a norm in that norm that we have given, right? So the remaining is this integral. So supremum of that over all t capital T, all s up to t is taken. Now this is precisely by the I should have used bold W and V here. Okay, this is bold W and V. This is by the Lipschitz continuity of f in the second argument. You have this, and this alpha that you have chosen here is precisely the Lipschitz, the Lipschitz constant that we had there, right? Right, we had an alpha here, right? So this is alpha, that is an alpha such that this happens, right? This is the alpha that we have chosen to choose the norm here, and that's the alpha that we are obtaining, we are using here, and that's what we have here, alpha W minus V alpha. Remaining is this integral, and this integral is precisely this value is less than or equal to this quantity, right? If you just integrate this, alpha times of this integral can be shown to be this, right? Because you know how to integrate e power alpha is derivative of e power alpha is alpha e power alpha. So you can integrate this as well, right? So integral of this, there's an alpha, this alpha will cancel out. Now if you take the values, if you take the limit values, you have this. So this is less than or equal to this, because all t's are coming from 0 to capital T. So from here we see that the alpha norm of this quantity is less than or equal to this, right, where this has become this. So this shows that T is a contraction, right? So since T is a contraction, then by the previous the contraction mapping theorem, we actually have a unique fixed point for T, right? And we have already seen that any fixed point of this T will be a solution for the first order equation that we have considered, right, this one. So we started with this, we had this T, we showed this is a contraction, so whatever is a fixed point here is a solution to this problem from the whatever we discussed in the previous lecture. So with this we have proved this result, okay. So the comment that I would like to make here is that, see, the proof is simple. Once we use the contraction mapping theorem, we have proved it, and by the uniqueness of the fixed point, by the uniqueness of the fixed point, you have a unique solution, okay. In this case, that's not a issue, that's not a problem. But in this process, you see, if you go back to the contraction mapping theorem, the fixed point was obtained by constructing a sequence, and the limit of the sequence was a fixed point. And that sequence was constructed starting from any arbitrary point, right, using the contraction property, if you remember the proof, right, from the previous lecture. So in this case also, when we say there's a fixed point for T, this fixed point, if we go through the proof of contraction mapping theorem, repeat that proof in this case here, we are going to get a sequence. We are going to get a sequence of functions which will converge to this unique fixed point of T, right? And that sequence can be, so you start with any arbitrary element in C0T, and you can use the contraction of T to obtain a fixed point. How did we get that? You start with any point, look at the image of that point under T, and then take that point as a second, so that value as a second, second element in the sequence, then look at its image, third element, and so on, right? That's how we constructed the sequence, which finally gave in the limit a fixed point. Similarly, this fixed point has such a sequence, and such a sequence is an approximation to this solution. So when we do numerics and other things, if you need to where we need to, because see, we have only shown a existence of solution here, right? We have not given a formula for the solution here. We have just showed that there is a solution. So that proof of the contraction mapping theorem actually gives you I mean, gives you a method to obtain the solution as a limit of a sequence of functions, right? That is coming from the proof of contraction mapping theorem. This is what is called, and that is what is called the Picard's iteration. So if you've heard of Picard's iteration, that is what it does, right? So all these today, with the benefit of hindsight, we can relate these things. But at the time of developing this theory, this was developed separately in separate specific instances or special cases. People developed different, which is why there is a Cauchy-Lipschitz, Picard-Lindelof. Everyone had contributed in some cases of this result. So in the modern general term, this is the proof, which is now a simple two-slide proof. Okay, so I have also motivated you the Picard iteration thing from this proof. Okay, though in this proof the Picard iteration is invisible because we are just showing existence, but the fixed point can be obtained like that, right, using that iteration. Now let's look at a special case, which is the corollary, that if so is a special case of f. In this case, it's called a linear system of ODE, right? Because this is a linear case. This is a linear case now. So the f that we had earlier has a special form. So this also has a unique solution. If it's if it's a special case, then it's a unique solution, right? We are going to just show that. So this is a special case because if f is at psi plus bt, so f in the second variable satisfies the Lipschitz continuity, Lipschitz property, right, where this alpha is supremum of mod at. So this falls in the previous theorem category. So one can actually claim that there is a unique solution to this problem. So you see now from the remarks that we made in the previous lecture, we have actually shown existence of a unique solution to a kth order initial value problem, where the kth order ODEs of the specific form that we started with, which is y power k equal to a function of all k minus 1 derivatives. So it's that kind of non-linearity. It's a special type of non-linearity, right? It is like it is linear in the kth derivative, but it can be non-linear in other derivatives. So it's that type of non-linearity. So we have shown existence of solutions, unique solutions for all kth order kth order ODE, IVP, the initial value problem of kth order ODE of the special type that we considered in the previous lecture, which includes the linear system of ODE also. Okay, now the question is, everything is fine, it's well and good, we have shown the existence, but can we relax this condition, right? The Lipschitz condition that we had on f, right? Because which means that we have an existence for restricted class. Whenever the data is Lipschitz in the second argument is only when you have a unique solution existing, right? So can we do in a much more general class, like can we do it? So we have to ask these questions, right? Natural questions. So can we relax the Lipschitz condition on f and assume, say, only continuity, right? We can, but in that case you can the way we got global solution, we cannot expect a global solution. We can probably get a local solution. When I say local solution, so the function that we obtain may not satisfy the ODE in the entire domain that we started with. It might be satisfying the ODE in some region of the domain. Okay, as an example, let's look at this first order non-linear equation, right? It's non-linear in the lower variables. In the highest derivative, it is linear, non-linear lowest variable, the kind of form that we had considered. So look at this initial value problem, right? Well, you can check that for this initial condition u0, this is a solution to this problem. Okay, so u0 over 1 minus u0 t will satisfy will satisfy this. In fact, when t equal to 0, it also satisfies this. So this is a solution to this initial value problem in the positive real line. Okay. The only issue is that you see this will not satisfy everywhere. The reason is because you see this solution can have a blow up when the value t, when t takes the value 1 over u naught. So u naught is already given to you. So whenever t is 1 over u naught, this is the denominator is 0 here, so you have a blow up for the solution here. So this solution blows up at t whenever t is 1 over u naught, where u naught is the initial value that is given. Can have a blow up. So only question is if this t belongs to the domain is a positive line. So for instance, if u naught is negative, then 1 over u naught is negative, which means t is negative, so it's not in the domain. So for u naught negative, suppose you start with a negative u naught here, then there is no problem. This IVP has a global solution, right? Whereas if the u naught is positive, then you have then 1 over u naught belongs to this belongs to the domain of this u, and hence there is a blow up of the solution at t equal to 1 over u naught. So you don't have a global solution, you have a solution for all h which is strictly less than 1 over u naught. Or you have to take intervals which are bigger than 1 over u naught. So either you take a connected or an interval which is contained in 0 comma 1 over u naught, or you should take an interval contained in 1 over u naught comma infinity. Okay, so you don't have a global solution as such, you have only a solution satisfied in certain regions of the original domain. So this can happen, and this is happening because the f that you have here, this is not Lipschitz. Okay, so we have relaxed that condition, and you don't always have a global solution. Things can vary, the things, right? Okay, so now if you take, this is again, if you take u naught is very, very large, then h has to be very, very small, and so on, which is of course obvious from here. Now if u naught is 0, right, because u naught can also be 0, which case this is not defined. So when u naught is 0, then 0 is the only solution, so you have a unique solution. So you see, when you relax this hypothesis f here from the relaxed kind of Lipschitz continuity here, then you actually have, depending on the initial value, you have all possible cases here. In one case it's global solution, one case is local solution, one case you actually have a unique global solution, and so on. So it depends on the initial value here. So this Lipschitz hypothesis seems to be an important hypothesis, right? You can't really relax it. The other thing is that relaxing hypothesis on the thing can also lead to non-uniqueness of solution, right? In the previous cases, we had a solution, one solution. But for instance, take this initial value problem. Okay, this is again not Lipschitz. In the positive domain, you take this problem IVP, then this is not Lipschitz when at 0. Okay, now whenever the initial value is not 0, you have this as a unique solution. You can verify that this is a unique solution to this problem whenever u naught is not 0. Okay, but whenever u naught is 0, then you actually have infinitely many solutions to this problem. For instance, trivially, u equal to 0 is one solution, u equal to t cube is another solution, and in fact for arbitrarily chosen t naught, if you define this kind of step function here, not step function but piecewise continuous function, then this is a solution to this IVP, and so on. So you have more than one. In fact, there is infinity, because you have a solution of, for every choice of positive t naught, you have a solution here. So you actually have infinitely many solutions here. You have, for every positive t naught, you have a solution. So you have as many solutions as you have real numbers, right? So this can happen. This is again because we relaxed the condition on the data f here. Okay, so we cannot relax it. So let's prove these results. Suppose we relax this condition. What is these examples telling you? That if you relax this condition, you can lack uniqueness and you may have a local solution and so on. So that's kind of that is kind of given by this theorem. So now we have relaxed the Lipschitz continuity, right? We just have the continuity in both the variables. Okay, here again, now what we have said is that there f was in the entire R, right? The second argument can be in entire R here. Here we have taken that f is given, defined on a ball of radius r centered at the initial value u naught. Okay, but that is only for technical purposes here. The idea of this thing is that when you relax the Lipschitz continuity to continuity, you have a local existence, right? That means, see, you started with a capital T like previously, but there exists a little h such that there is at least one solution, right? It says there can be more than one. So there is at least one solution, and that solution is a local solution. That is, it satisfies the IVP in 0h, not in the full domain, but there is some h such that in that region it satisfies the IVP. So it's a local existence. So this is a Cauchy-Peano theorem. Okay, so this is quite a bit involved proof. We'll do that. So again, the idea is same, that to solve this, to find a solution to this problem, we need to get a fixed point for a corresponding operator, right? So we will so we start with we'll choose the h later. So we have to show there exists a h, right? So we'll choose the h appropriately. So what we say, if we need to solve this for some h, in that h we need to show that this for that h we need to show that this operator t has a fixed point has a fixed point where this u will come from C10h, right? Basically this operator is defined in C0h, continuous functions on 0h, because we are looking for a solution in h. We are going to choose this h later during the proof. So showing an existence of solution to this is finding a fixed point to this operator t. Okay, so the idea here is to take this interval 0h, where we don't know h yet, we will do that later, but whatever that domain h that will come out later, that we are going to divide it into m so partition into m intervals of length h over m. Okay, so you make once you partition into m equal kind of m equal intervals, you will have an interval of length h over m, right? That's what we are going to do for this. And then you look at this initial value problem. So here you see it's a limit process, right? Derivative means it's limit of ut plus t ut plus h minus ut over h and so on. H or whatever. And don't confuse with this h, not this h. The definition of derivative tells you that u prime t is ut plus k minus ut over k, right? That is what it means. So that some quotient that comes in is equal to this. This is in the limit process, right? So what we do here is we do a finite difference approximation of this initial value problem. Okay, the way I had mentioned before, that the Cauchy-Lipschitz theorem actually gave you what is called the Picard iteration, right? So in fact, the proof of the Cauchy-Peano theorem is especially the Euler's approximation, Euler's method to approximate the solution, the local solution. Okay, we are not going to do it in this course. I'm just trying to connect it for you. So if you have seen Euler's method, that is the idea that is being used in this proof here, that kind of an approximation. Okay, so we partition this. So what we do is that we do a finite difference approximation of the initial value problem. So what is the finite difference approximation? Is this. So this derivative is written now in the sense of finite difference. Okay, so we are going to define new vectors ui. So you already start with you have a u0. Now you define u1. Okay, you define u1 such that you put I equal to 0. So you put u1 as u1 minus u0 over h over m. F of I is 0. So this is actually 0. That is the first. So if you see, when I divide 0 comma h into m intervals, the first interval is 0 comma h over m, and then the next interval is h over m comma 2h over m, and then 2h over m comma 3h over m, right? That is how we are going to get the intervals here, right? So the first endpoints are all, so the left hand side endpoints are I h over m, where I can run from 0 to n minus 1, m minus 1, right? So that's what we are trying to do here. So we are looking at the difference. We have a u0, we define u1 such based on this relation, right? This is precisely the, so you see this is precisely motivated from this IVP ODE here. U prime equal to f. In limit, this is like u prime equal to f, right? So you take the you define u1 as u1 minus u0 over h over m is f of 0 comma u0, and for u1 and for u2 it is u2 minus u1 such that f of h over m comma u1. Now for this to make sense, this should be in the domain of this second argument, because this is fine, this is in the interval 0 comma t, so it's fine, because if you recall, f is coming from f has a domain 0 comma t and ball of radius are centered at u0, right? So which means that when you take u0, the u1 is certainly defined. This second argument should be in the domain of f, and the second argument domain is the closure of the ball of radius r. So for this definition to be, for this ui plus 1 to be well defined, all ui's to be well defined, the previous ui should be in the ball of radius r. That is what we are going to verify now, whether this is well defined or not. So suppose I define ui plus 1 like this, then since u0 is in this ball, because this is a ball of center u0, so since u0 in this ball, u1 is well defined. There's no issue with u1. Okay. Now the question is, for u2, u1 should be in the ball of radius r centered at u0. So we need to verify whether for u2 to be well defined, whether u1 belongs to this ball, which means u1 minus u0 should be less than r. That is, the distance between u1 and u0 should be less than r. So we look at the distance between u1 minus u0. u1 minus u0 by definition, because u1 minus u0 is from this equation is h over m multiplied by this. So h over m multiplied by this, which is f of 0 comma u0. Okay, so u1 minus u0 by this definition is this. This is less than or equal to the supremum of f in the entire domain, that domain of, so m, this capital M is a norm of f, okay, in this domain. So this is a norm of f, which is capital M. So this is less than or equal to h over m capital M. Now if we choose, now yeah, I said we have to choose the letter h, right? So far we have not chosen h, right? We have to find an h such that some solution exists. So this h is so this h is chosen such that h is r is the radius of the ball which I started with, the domain of the second argument of f. So h is minimum of r over n comma t. So all these are given. R is given to us, t is given to us, m is the supremum of f. Okay, so So this H is minimum of R over M comma T. So if we choose H like that, so we have H over M comma M, but H over M is a partition of the entire interval H. So H is of course bigger than H over M. So this is Hm, but since we have chosen H such that it's minimum of R over M and something, so H is less than or equal to R over M, which means Hm is less than or equal to R. So we are choosing H such that this U1 is actually sits in this ball. Okay, so that's what we have done. So which means U1 is in this ball of radius R centered at U0, which means U1 belongs to the domain of F, which means U2 is well defined. Now the question is whether U2 belongs to this ball, so that U3 is well defined. Similarly, if you look at U2 minus U0, which by triangle inequality is U2 minus U1 plus U1 minus U2, with the same argument like we gave before and the same choice of H is actually going to give you that this so this is U2 minus U1 is Hm by L, this is Hm, like same like previous argument here, because it's all bounded by F, right, which is 2H over M, which is Hm, and H was chosen like that, so less than R. So similarly, U2 also satisfies, so U3 is well defined. If we can proceed along this way inductively, and we can show that all the Ui's that we have defined here are actually in this ball of radius R centered at U0. Okay. So now that we have obtained this sequence, now what we do is that for each M in the interval 0, if you let's explain, hopefully it works. So if you recall, if this is I'm sorry, this anyway, yeah, so I want to draw a straight line, nothing else. So what I'm saying is that so think of this as a straight line, okay, though I'm not drawing it straight because I'm not using, so this is 0 and this is H, right? So what we have done earlier is that we have made some M, we have just partitioned this interval into M, right? And the length of each of this is H over M. Okay, that is how we have done. So now we have M plus 1 equidistant points of equidistance point IHM, right? So this is 0, this is H over M, this is 2H over M, this is 3H over M, and so on. So what we have is M plus 1 equidistant points. And the way we have now defined M distinct vectors. Okay, we have M distinct, so we have a U0 which is coming from the problem. Using U0 we defined U1, U2 and so on. We have done this for up to M. So you have M distinct vectors Ui. When I say M distinct, actually M plus 1, but the U0 is already given to us. So we have defined M distinct vectors. So including U0 we have M plus 1 elements. Okay, so we have M plus 1. So what we do, and the original problem tells you the value of U at 0 is U0. Okay, so what we have is we have a value U0 taken at 0. What we are going to do is that we are going to give the value Ui each of this ui we are going to distribute on these endpoints. So we are going to we are going to define a function which has the value u0 at u at the first, which is h over m. It will take the value u1 and then u2, right, u3, whatever that value is, u3, and so on, right, and so on. This is what it's going to do. That's what we are trying to do now. So we have m distinct vectors. So that's what we are doing. What we have done, we are going to define a continuous function such that um is ui. That's whatever I drew and showed you, right? Right. So I have drawn and shown you right here. So we are going to define a new function from the interval 0h such that at these endpoints it takes the value ui, like here. So we are going to define a function which at these endpoints takes the value u0, u1, u2, u3, u4. Okay, and then, right, such that. So there are many ways of doing this. So what we are the way we are going to do is, so this is a function, and what we want is a continuous function defined in this interval such that at the endpoints it takes this value. So how do I define these continuous functions? So we are going to define, so suppose this is a value u naught. So I'm just going to join them by straight lines, right? So u0 to u1, u2, u3, probably u4, u5, u6, and so on. So this way I have a piecewise continuous function. This is my capital that I have defined, that I am defining in the next slide. So capital is defined like this. So as you increase m, the partition here increases, you have more ums, and in each stage I am just finding a function where at each the endpoints it takes these little ui's, and the function is just made piecewise continuous by joining these values. Okay, that is how we are defining the capital Okay, so we are piecewise joined within this interval IHM. Between joining this line and joining this line, piecewise joining, we have a continuous function which is capital UM. Okay, so now by whatever, if you write down the equation of whatever I just explained pictorially, that is just a straight line joining 2 points, right? And joining these 2 points, basically joining IHM comma UI to the another point I plus 1 h over m comma ui plus 1. So the line joining these two. So we write down these equations, so you actually have a formula for capital Um. Capital Um is precisely this function, where whenever so this is whenever t belongs to this interval, right? So this you do for each I. So for each I you have, so in this interval, in this range, this is the formula, the straight line joining these 2 points. Okay, that is my Now, but the way we have defined is a continuous function, there's no doubt about it, right? Because it's just piecewise linear construction, right? Piecewise linear. So it's a continuous function, and the subnorm of if you actually compute, the subnorm of is supremum over all ui, because the line is always joining from one ui to another ui. So the maximum of the function can be the maximum of ui's, right? It cannot take any maximum value between two ui's, right? So the supremum of capital is supremum of ui's. Okay, right, here, if this is a supremum, then that is one of the ui's, right? If this is the minimum, that is one of the ui. So supremum and minimum is one of these points. That is how we construct it. Okay, so now what is the supremum of ui? If I take any ui, if I add and subtract ui naught, then by triangle inequality we have this, but this ui's are always in the ball of radius r, so this is always bounded by u naught plus r, right? U naught is given to us, r is given to us initially from the domain, so all the ui's are bounded by this number u naught plus r, so this is uniformly bounded. So the sequence which is a sequence in the space of all continuous functions, is now an uniformly bounded sequence in the space of all continuous functions. Okay, so we have constructed a sequence of continuous functions which are uniformly bounded. Now we are going to show this sequence of functions capital Um are also equicontinuous. Okay, for that we just look at the value of Um at any point t and at the lower end point. So we know the value of, because it's piecewise linear in these intervals, right? That's how we constructed. So we look at umt for any t, suppose, and any t will be lying between these 2 points for some I, right? So you take any such t and you look at umt minus of the lower end point of that interval where t lies. So of IHM. Now this, by the way we define at this endpoint, it's going to take the value ui. So this is umt minus ui. Okay, and this is by this definition here, is equal to ui in this interval, right? So what we have now is umt minus ui, which is equal to this, right? And that's what we have said here. So this is equal to this, whatever is there, and that quantity is less than this is, and the way we have defined ui here, this is equal to f, right? So you actually notice here ui plus 1 minus ui h over m is f, right? And you actually have ui plus 1 minus ui h over m, which is right, sorry, this one, m over h is h over m here, so you have an f here as well. So if you use this equation, and this equation here, right, together, we can write this is less than or equal to this quantity, and this m is the subnorm of this quantity, so this is less than or equal to m. So this we have done for each t. So if you take for all s and t, umt minus ums is always less than or equal to mod t minus s m, right? This is always valid. So for any t here, you do similarly, you do any s, you do the same thing, but those whatever t minus something that you get, they are all anyway will be less than t minus mod s. So from this equality, from this inequality, you get this inequality. Okay, and this tells you that the sequence of functions are equicontinuous, right? This formula tells you that they're equicontinuous. This is independent of m, this little m here, right? So they are equicontinuous. So by Ascoli-Arzel also, something that we proved. So one application of that result. See, we are showing existence of a ODE using that result. So by Ascoli-Arzel result, this has to be this set has to be compact, right? This which is uniformly bounded and equicontinuous. So this is compact. So there is a subsequence to this sequence so let's call that subsequence uk, and it will converge uniformly to some element u. Okay, so this is from the Ascoli-Arzel theorem. So you have a limit, uniform limit for this subsequence, for some subsequence of this call that u. We are going to show that this is the u, this is the u which will solve that ODE that we started with locally in this 0h interval. which means we have shown a local solution. So we need to show this is u the solution. Basically, to show that, we need to show this u is the fixed point of the t that we started with. So we have to show that this u is the fixed point, which means we need to show that capital T actually just to not this T, domain T is different from this T. Okay, I should have used a different notation. I just realized now. So the T that you hear here, this is the domain T, some capital T, which is a number. Whereas the T that we have defined, that I defined here, this is an operator which is from the space of continuous function C0H to C0H. Okay, so don't confuse. That's I should have used, but somehow. So this T is different from this T. Okay, just a clarification. Okay, so this is an operator, but the situation will very clearly tell you what it is, but I should have avoided it anyway. Okay, so we will show that this u we have obtained as a limit is in fact the fixed point of the operator T. So we need to show Tu is equal to u. So for that, let's make some observations that actually happens. So just to show that, before that, first observe that, see, this by our definition was a piecewise continuous function. That is how we constructed it, right? So that piecewise continuous, so for that function you can actually write this as this integral. Why? Because see, if you have piecewise continuous, right, if I see our were like this, constructed like this, it will function like this, right? So if ums are like this, they are all differentiable except at these points, like forget one, they are all differentiable. So prime, if prime is actually a some kind of constant, right? Prime is actually a constant, and I can actually write as integral over these piecewise differentiable function. Okay, integral of this piecewise differentiable function. Okay, so just make this observation, right? There is no issue, and that piecewise differential and that derivative is actually a constant because they are all linear function, right? They are all linear function in that. So they are piecewise linear, so they are piecewise constant. So the derivative is piecewise constant. Okay, so actually has this form, right? We are going to get the precise form of this. So how do we get that? From the way we defined u, from the recursive relation that we started with. You remember the finite difference approximation that I wrote down? Let me just show you that again. In this, we have written down this. So you have ui plus 1. I can bring everything here, like I can take h over m here and ui that side. So ui plus m is equal to ui plus h over m of this. And apply the formula for ui. So recursively you apply it for ui. So you will now have a sum of terms here. Finally, you can end with u0 here, right? So you start with ui plus 1, replace ui for with in terms of ui minus 1, ui minus 1, ui minus 1 in terms of ui minus 2, so on. Then you will have a sum of terms here with the last term being u0, right? That's what I'm doing. That's what I'm doing here. So if you can write ui plus 1 as u0 as sum of some terms, right? Now what I do here, I can write this as u0 plus integral up from 0 to ihm of fm. What is fm? See, these are all just sum of some numbers, whereas these are the endpoints of that interval. So what we are doing here is that inside that interval, so to the right of the endpoint up to the next endpoint, next partitioning point, right? We just extend this function as the constant function, right? You understand what I'm saying? So what I'm saying is, see, you had this straight line interval 0 and h, you had these partitions you had these partitions. So now this is a value evaluated at some on these points, right? So what we are doing, whatever is the value f j plus h, we just give the same value this entire, that is extend constantly up to this point. Similarly, next and so on. Okay, so that's what I'm doing here. So this fm function is just taking the value f0 of u0. So whenever I equal to 0, you have f0 u0, right? So fm of s from 0 to the first hm is f0 u0. So in this interval, you have the constant function f0 comma u0. Okay. Similarly, in the next interval, you have f h over n comma u1 in this interval. Similarly, so that's what I'm saying here. Maybe one of them, maybe this should be strictly less than. Okay, so that there is no multi-valuedness. Okay, so yeah. Okay, so this fm function is this piecewise constant function. Okay, this fms is this piecewise constant. So this is sum over j, so I'm just extending it as a piecewise constant. So this is nothing but integral over IHN. Okay, so ui plus 1 is precisely u0 plus this. And we defined in terms of ui plus 1, so we actually have this capital to be this function, where it's summed over, integrated up to t from the same inequality here, because is, if you recall, see, was defined like that. Is ui plus this quantity, where ui plus 1. Now if I write ui plus 1 everything in terms of up to, extended up to u0, you will get the same incremental sum here, right? You have ui plus 1, write it in terms of ui, write ui in terms of ui minus 1, and so on. Finally, you will have something in terms of u0, right? If you write everything like that, the way we use the recursive relation here, you will get is u0 plus integral fms. This is, so basically what we said here in this slide is prime is what we have identified. So this prime is actually this piecewise constant function fms, which is in terms of the given data f. Okay, so is u0 plus this. So we have this property, this is true for all t up to h. So now we consider this limit of m going to infinity, tu minus We already know this u is a limit of uniform limit of So we look at tu minus. If this goes to 0, then we have shown that u is a fixed point, right? Because this is independent of m. So this goes to u. So what basically we are showing is tu minus u, right? So limit of m going to infinity, tu minus Now tu, there is a definition of this operator tu. So the definition of tu is also of some integral form, the first thing that we wrote down here. This one, tu is this, use this, which involves f, right? Which involves f, and this is in this form. So this u0 will get cancelled when you subtract. What remains is this integral. So what remains is integral of f, which is coming from t, and fm, which is coming from So this difference. Okay, so limit of m going to infinity. So this subnorm, becomes supremum over t. Okay, so this is the supremum norm, right? and supremum norm is over the argument of supremum is over argument of this u, which is s. So this is s, this s. Supremum over this argument, which is supremum over this argument. So limit of m going to infinity is supremum over this entire thing, where this f is a given f and this fm is the piecewise constant f. Now, as m goes to infinity, what is happening is when m goes to infinity, you are increasing the number of partitions of this interval 0h. Right? So, if you are increasing the number of partition of 0h, you are actually interpolating this f with finer piecewise constant function. Right? So, as m goes to infinity, what is happening is this is actually this is actually converging to f. Right? In fact, this f is uniformly continuous in both variables, and it's a continuous function on the compact set, right? So you actually have this convergence. This will converge. So fm will converge to f, and we already know that this um converges uniformly to u. So what we have is this side we will have 0. This side we will have du minus u equal to 0, which means du is equal to u, which means u is a fixed point. And that's precisely what we wanted to prove. Okay, so with this we have proved, we have shown the existence, both the global existence, which is the Cauchy-Lipschitz or Picard-Lindelof result, and the Cauchy-Peano, which is the Cauchy-Peano, which is the um, Cauchy-Peano theorem, which is the local existence result. Okay, and both are proved using the fixed point idea, that basically you look at the solution of a ODE as a fixed point of some operator and get a fixed point for that operator. The first, right, and we have used results like contraction mapping theorem, Ascoli-Arzelà theorem, and everything. We have made all these connections, right? So so the results that we do in a course on analysis has a very basically entire analysis grew out of trying to study differential equations. So we have made these connections, and also the connection that the global existence, the contraction mapping theorem proof was actually giving you what is called the Picard iteration, that is a Picard approximation of the solution of the ODE. Similarly, in this local existence, whatever proof that we have done is is actually the Euler method, which is the approximation that we do to obtain the local solution. Okay, so if you don't know Picard iteration and Euler method, then please have a look so that you can make a connection with this. Okay, then I'll see you in the next lecture. Thanks a lot.